This formula is also known as the DUH factor. Basically, you need to gather information from pressure gauges mounted to the existing system. With the previously mentioned formulas, the friction head and the velocity head are estimated in the initial phase when everything is new. The Backus and Custodio method measures the exact friction head and velocity head in any existing system. It doesn't matter when your system was built. The Backus and Custodio formula is shown here, where delta P is the pressure differential from an upstream to a downstream gauge in a section of a pipe. dr is the discharge running, the discharge piping with the pump running. do is the discharge off, so the discharge piping with the pump not running. sr is the suction running, the suction piping with the pump while running. so is the suction off, or the suction piping with the pump not running. 2.31 is the conversion factor between psi and feet of elevation, and SPGR is the specific gravity. In general, the friction head and the velocity head are observed while considering the system. We'll see this further ahead. The friction head and the velocity head are the reasons that companies contract civil engineers to design their new plants. Years later, those design parameters have changed due to erosion and other factors. Let's now take a look at the following configuration. Pumping a liquid from one tank into another. This system, although simple, with only one pump, is more or less representative of all systems. This system is composed of 180 feet of pipe, 40 feet of 6-inch suction pipe, and 140 feet of 4-inch discharge pipe. This system piping uses fittings with bolted flanges. The 6-inch elbows have a K value of 0.28. The 4-inch elbows have a K value of 0.31. The 6-inch gate valves have a K value of 0.09. The 4-inch gate valves have a K value of 0.15. The 4-inch globe valve has a K value of 6.4. The 4-inch check valve has a K value of 2. The 4-inch tramp flanges have a K value of 0.033. The 3-inch flange has a K value of 0.04. The sudden reduction has a K value of 0.5. The 6 to 4-inch eccentric reducer has a K value of 0.28. The 3 to 4-inch concentric increaser has a K value of 0.192. The sudden increase has a K value of 1. The required flow in this example is 300 gallons per minute. The K values that you can see here are provided by manufacturers and can be found on charts provided by different organizations. The goal of this example is to apply the formulas, the K values, the pipe friction losses to determine the friction head, the velocity head, the static head, the pressure head, and then to calculate the total dynamic head of the system. And once we do that, we can specify a pump for this particular application. Now, one component of the total dynamic head is the static head. In this example, the surface level in the discharge tank is 115.5 feet above the pump center line. The surface level in the suction tank is 35.5 feet above the pump center line. Therefore, by observation, the static head in this example is 80 feet. Another component of the total dynamic head is the pressure head. We can see from this figure that both tanks have vent valves. These two vessels are exposed to atmospheric pressure, which is the same in both tanks. So by simple observation, pressure head in this example doesn't exist, and therefore HP is equal to 0. Now we know that the flow is 300 gallons per minute. We have the diameters of the suction piping and discharge piping, therefore we can calculate the velocity of the fluid in the discharge and the suction piping. And these velocities are seen here. Now using the formulas, the K values and the velocity values, we can estimate or calculate the friction and velocity heads in the system. Because the velocity head is used to calculate the friction head, then we'll begin with the velocity head. The formula to calculate the velocity head is shown here. So basically, it is the velocity head of the section plus the velocity head of the discharge. And recall that the formula for the velocity head is the velocity squared divided by 2g. So this means that the velocity head of the system is equal to the suction velocity squared plus the discharge velocity squared divided by 2g. Substituting for the known values, we then have the following. So the velocity head of the system is equal to 1.06 feet. The suction and discharge velocity head values will be used in the friction head formula, which is seen here. So the friction head of the system is equal to the sum of the individual friction heads in pipes, elbows, valves, flanges, and others. Taking this formula in groups, we begin with the friction head in the pipes. The friction head in the pipes are equal to the friction head in the suction piping plus the friction head in the discharge piping. To calculate the friction head in a pipe, we will use the formula we have seen in the previous section. So it is basically the K value times the L, which is the actual length of the pipe, divided by 100, and we apply that for both the suction and discharge. So here, substituting for the known values, we then have the following for the friction head in the pipe. So roughly 2.9 feet. Now we calculate the friction head in the elbows, and the formula is seen here. So the friction head in the suction elbows plus the friction head in the discharge elbows. And recall, to calculate the friction head in this case, we will use the following formula. So the K value times the velocity head. We'll apply that to the discharge and the suction. Substituting for the known values, we then have the following. So the friction head in the elbows is equal to 0.9 feet. Next, we calculate the friction head for the valves. So with the same methodology, it is equal to the suction friction head plus the discharge friction head. In our system here, we have 5 valves. There are 2 6-inch gate valves in the suction pipe, 1 4-inch gate valve, 1 4-inch globe valve, and 1 4-inch check valve in the discharge pipe. So the formula is the following. The K value for each type of valve times the associated velocity head. And we apply that to both discharge and suction piping. Substituting for each term, we then have the following. So the friction head for the valves is equal to 7.6 feet. Next, we calculate the friction head in the flanges. In our system, there is a 6-inch tramp flange on the suction pipe with the tank and a 4-inch tramp with the pump. There is a 3-inch tramp flange at the pump discharge and another 4-inch tramp at the discharge tank. So the formula to calculate the friction head is equal to the K value times the velocity head. Now, substituting for the known terms, we then have the following. So the friction head in the flanges is equal to 0.007 feet. This is clearly an insignificant number. With only one pump and less than 200 feet of pipe in our system, there are only 4 flanges. But think of it this way. Imagine an oil refinery with 20,000 pumps and thousands of miles of pipe and equipment on site. Imagine the number of flanges in this case. Imagine also the number of flanges in the firewater system in a skyscraper building. In a real set of circumstances, the friction head values through flanges could be significant, and they would have to be calculated to specify the correct pumps. Last, we need to calculate the friction head losses through other connections in the piping. In our system, we have a sudden reduction in the suction between the tank and the piping. There is an eccentric 6 to 4 inch reducer between the suction pipe and the pump. There is a concentric 3 to 4 inch increaser from the pump back into the piping. And finally, a sudden enlargement going into the discharge tank. The formula to calculate the friction head losses associated to these elements can be seen here. To calculate each of these terms, we multiply its K value by the velocity head, as seen here. And so the friction head losses for these elements is roughly equal to 1.2 feet. Now we have all the information to calculate the friction head in the system. Substituting for the friction head in the pipe, elbows, valves, flanges, and others, we then have the following. So the friction head in the system is equal to 12.6 feet. Now we are almost finished, but as you can see, a lot of mathematical gyration required just to determine the velocity and the friction head. This is a lot of math for just one pump. Imagine the work to specify pumps for a refinery, petrochemical plant or chemical plant, or municipal water system. Now you can see why governments and refineries and chemical companies contract consulting engineering company to do this work and specify the pump. Now that we have calculated the static head, the pressure head, the velocity head, and the friction head, we can easily determine the total dynamic head. Recall that the total dynamic head, or TDH, is simply the sum of all these components. So substituting for each head, we then have the following value for the total dynamic head. So it is roughly 94 feet. This means that this system requires a pump with a best efficiency point of 94 feet. Recall that for a system or for a pump to work properly, the total dynamic head should be equal or near the best efficiency point. And we know that this system requires a pump that can deliver 300 gallons per minute. Now that we have the value of the best efficiency point, and we know the flow for the system, we can use the family curve to determine more design characteristics of the pump. So let's see how we can do that. This is a family curve for a conventional centrifugal pump used in the chemical industry. This pump is designed to operate at 1800 RPM. We can see from the head capacity curve that this pump could match the requirement of our system. The flow we're looking for, 300 gallons per minute, is possible to achieve. And a head of 94 feet is also included in the performance of this pump. So as you can see here, with 300 gallons per minute flow and 94 feet head, the design point or operating point of our system is located here. This means that the best pump design that will fit our system requirement is a pump with a shut-off head of 100 feet, an impeller size of 10 inches, and a 15 horsepower motor. Also, we can see from the family curve that operating our pump at this point would give a pump efficiency between 60 and 65%. So, if this pump were bought off the shelf from local distributor stock, it would be probably a 3x4x12 model end section centrifugal back pull-out pump, with the impeller machined to about 10 inches before installing the pump into the system. And that's the way it is done for a new installation. If the system already exists and the equipment is running, we can recover the friction head and the velocity head from gauges using the Backus and Custodio method, and forget about all those calculations. Take a look at this configuration here, with the corresponding placement of pressure gauges installed into the piping numbered 1 through 5, and the corresponding elevations. In this system drawing, pressure gauges 1, 2, and 3 are in the section piping. Gauges 4 and 5 are in the discharge piping. With the system and pump turned off, we would open the vent valves on both the suction and discharge tanks. This assures that both sides of the system are atmospheric and then cancel the pressure head. The discharge tank and all piping should be full with water for the test, or if required with the pumped liquid. Remember that gauge readings will be adjusted by the specific gravity. Expel all air bubbles in the piping. Some pumps have a little petcock valve to allow expelling any trapped air in the volute. On the pump, conventional stuffing boxes can also trap air. This must be expelled too. Vertical valve stems in the piping can trap air, so loosen the packing to expel this trapped air. This is done so that there is a complete column of liquid from the top to the bottom of the system. Air pockets and bubbles might cause inaccurate pressure gauge readings. All valves in the column, including the check valve, should be opened, except for the gate valve between gauges 1 and 2. It should be closed to hold the column of liquid and prevent draining the line. Now, here is a quick reminder or review of the Backus Custodio formula. Let's take our readings with water as the test liquid just to keep the conversion simple. With the system and pump off, note that gauge 5 should be reading 20 psi. This is because it is 46.2 feet below the surface level in the discharge tank. Gauge 4 should be reading 50 psi. It is 115.5 feet deep into the column. The difference between gauges 4 and 5 is 30 psi, so the term delta PDO in the Backus Custodio formula is equal to 30 psi. In the suction line, note that gauge 3 is also reading 50 psi. It also has 115.5 feet of liquid elevation on it. Pressure gauges 2 should read 60 psi because it is 138.6 feet deep into the column. This indicates that the term delta PSO from the Backus Custodio formula is equal to 10 psi. Now, gauge 1 on the other side of the closed valve is reading the elevation in the suction tank. This gauge should be reading 25 psi because it is 58.6 feet deep into its column. Now open the gate valve between gauges 1 and 2. Start the pump and relieve the check valve if it is being mechanically held open. Permit the pump to run a few minutes to stabilize. We'll continue to note pressure gauges readings with the system functioning. Because all valves are now open, gauge 1 becomes our upstream gauge on the suction line. With the pump running, all activity on the suction side of the pump is separated from the activity on the discharge side of the pump. Gauge 1 continues to read 25 psi. Gauge 2 should also read 25 psi. Gauge 3 should now be reading 15 psi because this gauge is 23.1 feet above gauges 1 and 2. However, in reality, gauge 3 is recording 13 psi with the system running. So the term delta PSR from the Backus and Custodio formula is equal to 12 psi. Recall that this term corresponds to the pressure differential at the section when pump is running. In our case here, it is the pressure reading on gauge 2 minus the real pressure reading on gauge 3, so 25 psi minus 13 psi, so equal to 12 psi. Now we consider the pump. We have already discussed that the pump takes the energy that the suction gives to it. The pump adds more energy, jacking the energy up to the discharge pressure. In this case, the pump is designed with the best efficiency point of 94 feet, which also is the total dynamic head of the system. The 94 feet indicates that the pump can generate about 40 psi. Recall that to convert head into pressure, we multiply the head by the specific gravity and we divide by the conversion factor 2.31. So here 94 feet times 1, which is the specific gravity of water, divided by 2.31 gives 40 psi. Now the suction pressure is 13 psi. So the discharge pressure gauge number 4 should be reading 53 psi. That is 13 psi suction pressure plus 14 psi the head developed by the pump. With gauge 4 on the pump discharge reading 53 psi, gauge 5 should be reading 30 psi less or 23 psi. This is because gauge 5 is 69.3 feet above gauge 4. However, by observation, gauge 5 is only reading 18 psi. Therefore, the term delta PDR, so the pressure differential at the discharge when the pump is running, is equal to 35 psi. That is the pressure gauge reading on gauge 4 minus the real pressure reading on gauge 5, so 53 psi minus 18 psi. Now we have all the information we need to insert into the Backus and Custodio formula. Substituting for delta PDR, delta PDO, delta PSR, delta PSO, and for the specific gravity, which is equal to 1 because our test liquid is water, we then have the following for the system friction head and velocity head. And this is equal to 16.17 feet. Let's now discuss this method. The Backus and Custodio formula does not make mistakes. It is not based on models or experiments developed 150 years ago. It doesn't depend on valves being completely open. It doesn't depend on the specific instructions regarding equipment assembly. It doesn't depend on new piping, and it is not based on water. It depends on the actual piping and all the system fittings, as they are now, and the next shift, and tomorrow, and next month. If a resistance load changes, it will be registered on the gauges. If the pipe diameter changes, it is recorded on the gauges. If new equipment is added, it is visible on the gauges. The pressure gauges and other instrumentation are the pump's control panel. You wouldn't drive your car without a dashboard. Now, regarding pump failure, problematic sieves and bearings that need emergency maintenance, in about 80% of all cases, the pump was telling the operators what the problem is, hours, days, and weeks before the failure even occurs. What is really happening is that no one is interpreting the information on the gauges. This detailed discussion on the friction head and velocity head probably has you ready to throw this course into the garbage. But really, this method is a powerful tool to know the characteristics of your system. With the Backus and Custodio formula, the differential pressure gauge readings on the system with the pump turned off will cancel any elevation changes existing in the system. Exposing both sides of the system to atmospheric pressure cancels the pressure changes. And then, with the system operating and the pump turned on, the further differential gauge readings will record the velocity head and the friction head that are being lost in the system. Remember that the other resistance approximations, so the Hazen and Williams formula and the Darcy formula, are only valid in the first few hours or days of service. The system begins to change once the pump is turned on and production begins. Operators open and close valves to meter the flow through the pipes. Filters and strainers begin to clog. Inside pipe diameters form scale. Or new equipment is installed or other changes occur with maintenance. So the equipment loses its efficiency. For this reason, my advice to you, if you want to accurately determine the characteristics of your existing system, regardless of when it was built, is to install gauges on your pump and piping system. Teach the operators and maintenance personnel to interpret the information as we have done with this last example. The configuration on which we have applied the Bacchus and Custodio method that you can see here, although simple with one pump, is more or less representative of all systems. So it wouldn't be difficult for you to reproduce it on your existing system.